The next type of distribution we're interested in looking at in statistics is what's called the binomial distribution. So a binomial distribution consists of repeated Bernoulli trials. So similar to what we saw yesterday with our binomial probability. X will represent the number of successes in n Bernoulli trials. And so the formula for probability of x equals x turns out the same as we saw yesterday because it is essentially binomial probability. So NCX, probability of success to the power of x, probability of failure to the power of n minus x. So P is probability of success, x is the number of successes we're looking for, n is how many times we repeat the trial. Well, let's draw that up into a frequency distribution table. In this case, we've got n trials, so I put in a box for 0, 1, 2, but we would have one all the way up to whatever the last one is, n. And each one of those, the probability would be a binomial probability, and we have our formula to work that out. Next row, of course, is xpx, so I multiply each of those by x, and then x squared px, I multiply it by x again. So our expected value will be the sum of the xpx row. So the sum of all those terms. We would end up with the sum of the general term would be k, nck, p to the k, q to the n minus k. Now, I know that very first term obviously is going to be 0, because when you sub in 0, 0 times nc0 is going to be 0. So I'm left with just the sum from 1 to n of k nck. Now that sum I could end up rewriting, because nck would be n factorial on k factorial, k minus 1 factorial. So the n factorial, I could factorise the n out, leaves me with n minus 1 factorial on the top, but then the k would cancel with the k factorial on the bottom, leaving me with k minus 1 factorial. So in effect, we end up with n times n minus 1 c k minus 1, and we'd still have p to the power of k, q to the power of n minus k. Now, why on earth do that? Well, because now I can factorise out n. N's a constant, so I can pull that out of the sum. I'm also going to pull out the p, so I'm left with, now have a look at the powers, p to the power of k minus 1, q to the power of n minus k. They add up to be n minus 1. So what I've got is the general term. Now, it's not quite the full expansion, because we would want from k equals 0 to n minus 1. Well, that's okay, because I've got k equals 1 to n. I just got to change the pronumerals. Everywhere I see a k, replace it with k minus 1, and I get the new sum there. I'm going from k equals 0 to n minus 1 of, and now I've got the general term. So in fact, what we've got is np times q plus p to the power of n minus 1. But q plus p, well, that's equal to 1, because they were the probabilities. So it's simply np. Don't panic yourself about the derivation of that. All you really need to know is the expected value is going to be np. But that's how we get it. We can prove that to be true. All right then, well, let's do the same with variance and see what we come up with. So it's going to be the expected value of x squared minus the expected value squared. Well, I'm going to play around with the expected value of x squared. I'm going to rewrite that as x times x minus 1 plus x. Whoa, why do that? Well, I can play around with the expected value again. We know what the expected value of x is. So I can rewrite it as expected value of x times x minus 1 plus the expected value of x, which we know to be np. And of course, we're still subtracting the n squared p squared. Now, what is the expected value of x times x minus 1? Well, that'll end up being the sum from 0 to n of k minus 1, and then times our binomial term there, nck, p to the k, q n minus k. But if I pull out k equals 0 and k equals 1, both of those would be equal to 0. So I'm left with the sum from 2 to n. Now I can play around with this one, similar to what I did when we looked at expected value. And we will end up with n minus 1 p squared. It takes a few steps to get there, but if you follow it through, you'll see that's what we get. So n minus 1 p squared. But that's just the expected value of x times x minus 1. Let's put that back into our variance of x. Remember the stage we'd got that to. It was expected value of x, x minus 1, that thing we just worked out, plus np minus n squared p squared. Okay, bit of algebra now, and we can now show that the variance is simply npq. So a very simple little formula, npq. And again, that's all you really need to know. If we have to work out the variance of a binomial distribution, npq. So let's summarize that. If x is a binomial distribution, so a binomial distribution we summarize with bin for binomial, and then the two things we're interested in are the number of times we're going to do the trial and what the probability of success is, so n and p. Now, once we know those numbers, the expected value of x will be np, the variance of x will be np, 1 minus p. If the probability is less than a half, we'll end up with a distribution that is positive skewed. If it's equal to a half, we're going to have a lovely symmetric distribution. And if it's greater than a half, then we'll have something that's negative skewed. Well, let's have a look at this example. We have to state whether a binomial distribution could be used in each of the following problems. Now, if the binomial distribution is acceptable, we'll define the random variable and state the different parameters. Okay, so the first one we got. A fair dice is rolled 10 times. The probability of getting 3 4s, 4 5s, and 3 6s. Now, this is not binomial because we've got 3 different outcomes. Remember, we said a binomial or a Bernoulli trial could only have 2 possible outcomes, 0 and 1. Probability of success, probability of not success. So, no good. That one's not binomial. Now, if we wanted to just find the probability of 3 4s, that'd be binomial because we're interested in one thing there and it's going to either happen or not happen. We'll get 3 4s or we don't. Success or not success. And similarly, if we just ask for 4 5s or 3 6s, that would be binomial. So a binomial distribution, 2 possible outcomes. The thing you're looking for succeeds or it doesn't succeed. So part B, a fair coin is tossed until a head occurs. Find the probability that 8 tosses are necessary. No good. Because we don't know how many trials. Remember, we defined the binomial distribution. There were 2 things we were interested in. How many times are we going to repeat the experiment? And what the probability of success is. In this case, we don't know how. I mean, theoretically, you could toss the coin an infinite number of times before 8 tosses come up. So that is not binomial. The random variable is the number of tosses. That's what we're interested in. We don't know what the number of tosses is. A jar contains 49 balls numbered 1 to 49. 6 of the balls are selected at random. Find the probability that 4 of the 6 have an even number. This now depends on whether selections are made with or without replacement. If it's without replacement, no good. Binomial probability, you'll recall we said, had to be with replacement. The probability has to be the same every time we do the trial. If we don't replace the balls, then the probability will change every time we pull a new ball out. So that one would not be. But if it is with replacement, this one's fine. It would be binomial distribution. So X, our random variable, would be the number of balls with an even score. That's the thing we're interested in looking at. We know how many times we're going to repeat the trial, and we know the probability. So the parameters here, X, it would be binomially distribution. 6, we're pulling 6 balls out, so we're going to repeat the trial 6 times. The probability of an even number, well, if we've got numbers 1 to 49, there's 24 even numbers there, so that's 24 out of 49. And we could work out then probability that X equals 4, sub into our binomial probability formula. So the binomial coefficient, 6C4, probability of success, 24 and 49 to the power of 4, probability of failure to the power of 2. And there's a nice, well, unsimplified answer. The numbers are way too large to write as a fraction, so I'll approximate that to 4 decimal places, so 0.2247. Okay, part 2, okay, example 2. So we know it's a binomial experiment, they're telling us that. The probability of X successes is as follows. So they've started the distribution table for us. Probability of success at one trial. Okay, well, what do we got? We know we're doing it 3 times. P is what we're trying to find here. They're the two things that define our binomial distribution. We want to find one of those, so P. Well, probability of X equals 3, they've told me, is 0.027. So write that as a binomial probability. I'll have 3C3, the binomial coefficient. Probability of success, which we're trying to find, would be to the power of 3. Probability of failure would be 1 minus P, that'll be to the power of 0. That's the equation we need to solve. So P cubed ends up being 0.027. So the probability of success for this particular experiment is 0.3. So what would be the variance then? Well, now I just substrate into that formula. Remember, we don't have to derive it. The formula for variance of a binomial distribution is NP 1 minus P. 3 times 0.3 times 0.7, 0.63. All right, let's have a look at some graphs. So each of these are either positively skewed, negatively skewed, or symmetric. Which one is which? Well, A is the symmetric one. There it is. We can see the peaks nicely in the middle. Now, which way around? Positive skew and negative skew, B and C. I always think they're the wrong way around because I always think positively skewed, we should be towards the positives, but it's actually the other way around. So B is negatively skewed and C is the one that is positively skewed. Which distribution is most likely to have an individual trial with a probability greater than pi on 5? Well, that's all to do with probability of half would be symmetric. Are we less than a half or are we greater than half? Well, what is pi on 5? Well, pi on 5 is actually bigger than a half. So B would be the particular one we're looking at. It'll be a negatively skewed graph. Another example. X is a random variable. Its distribution is defined this way. We're going to repeat the trial 150 times. The probability of success is 2/5. Let's find the mean and standard deviation. The mean was n times P. So 150 times 2/5, 60. The expected value is the mean. The variance for this one turns out to be 36. Remember, standard deviation is the square root of variance. So the standard deviation for this one is 6. So how many more trials would we have to do to increase the mean to 100? Well, if I want the mean to be 100, then n times P would have to equal 100. So n times 2/5, n would have to be 250. But the question didn't say how many trials, 250. It said how many more. We've already done 150, so we'd need another 100 trials. Now, how would that change the standard deviation and its overall distribution? Our variance now becomes 60. The standard deviation is 7.75. So how does that affect the distribution? The data is now going to be more spread out because the deviation is larger. And the deviation is a measure of spread. So how far away from the average are we? So our data is going to spread out. We've devised an experiment. 2 dice are going to be rolled 10 times, and the number of times the sum equals 7 is noted. What is the mean and standard deviation of this distribution? So X is going to be the number of times the sum is 7. It is a binomial distribution because either the sum is 7 or it's not. So success or failure. We're going to roll the dice 10 times, so n is 10. The probability that the sum is 7 turns out to be 6 over 36, which simplifies down to 1 on 6. So the mean, NP, 1.67. And, well, the variance is 1.3889, so the deviation, 1.18. Now we're going to simulate an experiment 1,000 times. So I used a spreadsheet and I came up with these results. So they randomly picked numbers for me. So there's a simulation for rolling those 1,000 times. So what is the mean and standard deviation of that simulation? Okay, well, the average would be the sum of X times the relative frequency, that particular row. So 1.633. The variance is 1.500311. Deviation 1.22. Draw the simulation and the experimental frequency polygon on the same set of axes. Well, there you go. Again, I use my spreadsheet to draw it for me. But the blue one is our simulation. The orange one is the theoretical one. So what we were expecting to get. They're actually reasonably close. It's not a bad simulation. What we should see is the more times you repeat the experiment, the closer and closer to those curves actually matching. Okay, 17b, we'll play with binomial distribution.